Hi everyone, my name is Peter Rohde. Thanks very much for inviting me along to this. Today I'd like to talk to you about some work we've done recently on distributed consensus using quantum proof of work. And the context here is that we're thinking about blockchain technology, where we're aiming towards decentralized finance and the ability to log financial transactions in an honest way where there isn't a trusted central authority like a bank or a financial institution to actually be notarizing those transactions. And so the whole point of decentralized finance is to address that problem. How do we do this in a secure way without a central authority? And the very original Bitcoin protocol that started this whole wave of blockchain technology that we've seen in recent years was built on a particular way of solving this problem called proof of work. And proof of work has been a fairly controversial headline lately. Firstly, it's very revolutionary because it's enabled so many blockchain technologies, but at the same time, it's been getting a lot of criticism because of the amount of energy that it wastes. And we wanted to see whether quantum advantage could be an advantage in this type of context. And that's what this talk is all about. So distributed consensus is really about saying we've got some network of parties. We don't necessarily know who they are, and they're not necessarily trustworthy either. There could be liars amongst them or people conspiring to make false transactions. And so the goal is we've got a network of people. We want some kind of majority vote to honestly represent what is the actual source of truth. And the context for wanting to do that is specifically in the context of a blockchain. So this is the sequence of how a blockchain transaction takes place. First of all, some node on the network makes a transaction request, and the goal is for that transaction to be approved, and in doing so, it gets added to the blockchain. So that new block that's sent out to the network, and all of the other nodes in the network can evaluate it and ask themselves, is this a legitimate transaction or not? For example, they might look at the wallets of the people that are transferring money away and say, do they have enough money to be able to make this transaction? That would be one simple criteria if it was just a simple monetary transaction. And then some magical algorithm has to take place where those nodes in the network reach some sort of honest agreement on whether to approve a transaction or not. And if it's approved, then it gets added to the blockchain and it becomes permanent and you can't change it anymore. So the way that this has been done in the Bitcoin protocol and many other protocols since is using proof of work. And what this really is a distributed algorithm for randomly choosing a small number of nodes from a very large network, which could have an indefinite number of participants in it. So first of all, why do we want to solve this problem? Why do we want to randomly choose a small number of nodes from the network in order to be representative of the honest majority? The reason we want to have a random selection of nodes is to prevent any kind of strategizing by dishonest nodes. So if we look at this, these two pictures on the left, they both have the same percentage of red and blue elements in that set. It's just that in one case, they're all clumped up on one side together. In the other case, they're randomized around the place. So consider that first one. Suppose you weren't randomly choosing nodes from the network, and they just had a fixed arrangement like this, and we knew which fixed subset of the nodes were going to be performing a transaction, or validating a transaction. Then what could happen is all the dishonest parties, they could conspire together and say, let's get ourselves in on that minority corner in such a way that we can get a false majority and overthrow the will of the network and make a false transaction. If we randomize all of the locations of all of the nodes so that when we choose a small subset of nodes, it's guaranteed to be random, then no strategizing is possible anymore. Randomness erases any kind of strategy that you can do to try and manipulate or gerrymander how you work your way into that notarizing set. Now, the way proof of work does this is a very clever one. The idea is that they use as a primitive what's called a cryptographic hash function. And a hash function is a function that we use very, very often in modern cryptography, but there are a few properties of it that are particularly useful to solving this distributed algorithm of randomly choosing a small number of nodes. So a hash function has the following properties. Firstly, it's a one-way function. So if I've got this function f of x goes to y, x is the input, y is the output, and it's a one-way function in the sense that if you know what x is, you can very easily evaluate the hash function to find the output. But it has what's called pre-image resistance, which means if you know the output, you cannot efficiently figure out what the input could have been. In other words, if I give you y, you can't figure out x so easily, but you can do it the other way around very trivially. And the final property is that it's pseudo-random in nature. So if you take a value of x and evaluate the hash function to get the associated value of y, if you make even a little change, a single bit change to x, it completely changes what y is. So it really scrambles things up in a very unpredictable and random, quasi-random kind of way. So proof of work, what they call mining, when you try and participate in proof of work, it uses this hash function in the following way. We say, let's have a look at the header from the previous block. So the header is just a digest of what the previous transaction was. We want all of these transactions to be chronologically linked so that they form a well-defined order. So we look at the most recent transaction, have the digest representing that transaction, and then we concatenate it, that's the vertical bar, concatenate the header with some input x and evaluate that hash function to get an output value of y. And we're going to say that you successfully mine the coin, or in other words, solve this problem, if the output y satisfies some constraint. So it's less than a certain number or has a certain number of trailing zeros, some arbitrary constraint that you can adjust how tight that constraint is, which we call the difficulty, which relates to the likelihood of actually succeeding it if you just choose an arbitrary value of x. So miners, they sit there and they take a value of the header that they're trying to add a new transaction subsequent to, and then they just repeatedly try different random values of x until they get an output y that satisfies that particular constraint that makes it, give it a certain success rate. And the point is that because of the pseudo-random nature of hash functions, you really can't rig this. There's no easier way to do it. To find a value of x that gives you a satisfying value of y, the best you can do is just literally randomly choose x, try it. If it doesn't work, choose another random value of x. And so it's just this process of repeatedly trial and error on this random type of function until you get an output that satisfies a constraint. And then when you succeed at doing that, you've successfully mined that transaction. In other words, you get a reward and you're considered a winner, and now you participate in notarizing that transaction. So the reason that they do this is because we're dealing with a network where we don't have identities associated with the players. So these are all unknown nodes. It's a completely open environment. And there are different ways of solving it in other contexts, but in the context of an open environment, this algorithm is essentially as reasonable as you can get in solving this problem. From a group of unknown nodes, how do we randomly select a small subset of them? This solves the problem, but as you can see, it's inefficient because it involves all this trial and error. And the inefficiency is a really big problem with blockchains at the moment that use proof of work. In this figure on the left are some actual real-world numbers taken earlier this year, showing the amount of network energy and environmental overhead associated with mining a single transaction on the blockchain. So 368 kilowatt hours, or a third of a kilogram of electronic waste, just to do a single transaction. So this is hugely inefficient when we've got these astronomical global networks of all of these people competing, and we need to make a small number of them succeed. that means that the vast majority of them are working for nothing. And so the whole thing is very, very inefficient. And you'll have seen headlines these days talking about things about Bitcoin using as much energy as Greenland or Sweden or some other medium-sized country. It's no exaggeration because there are that many participants in these networks, all just repeatedly wasting all of these compute cycles to try and win this artificial game. So here's the top proof of work cryptos around at the moment. I don't even know most of these myself, but we all recognize Bitcoin at the top. All of these use this mechanism of randomly selecting a small number of nodes to notarize transactions. They already make up a significant fraction of the global crypto market, and the energy consumption of all of them combined is quite astronomical. So to address that problem, people on one hand are looking at other ways of doing things aside from proof of work, and the Ethereum network recently made a transition to proof of stake, which is regarded as less secure, but it's a much more efficient way of solving this problem. So there are trade-offs. We didn't want to make that kind of trade-off, trading away security for something that's faster. We wanted to look at a different avenue. Instead of wasting all these compute cycles on hashing random data, let's do it differently and instead see what happens if we introduce quantum algorithms into the mix. Now, the people doing this classically, they're investing a lot of money into doing this. This is a piece of hardware you can buy off the shelf for $9,000, and it pumps out over 160 terahashes per second and consumes 3.5 or 3.1 kilowatts of energy. This is something you can run in your home to contribute to these Bitcoin mining networks or similar networks. We want to avoid all of that and say, can we do something without hash functions, but something quantum instead? And so this leads to our notion of quantum proof of work. So first of all, what do we need to make that work? The first thing we need is a hard problem that can be easily verified. So that's exactly what hash functions did. They're hard to invert. That's the hard problem, finding a satisfying input, but they're easy to verify in the sense that once you know what the satisfying input, it's trivial just to evaluate it and check that it works. But we don't just want that. We want something that has some kind of quantum advantage where hopefully once we churn through all of the numbers, it turns out that there's a efficiency improvement. And we'd really like to be able to do it using some kind of quantum hardware that's available today. In the quantum computing community, there's a notion called NISQ, which means noisy intermediate scale quantum computers. Really what this refers to is the sorts of quantum computers that we have today and that we're probably likely to be restricted to for quite some time until full-fledged quantum computing becomes available. So all of the headlines we've read about recently, where people talk about quantum supremacy or quantum advantage, where one supplier or another has built a new quantum computer that can do X so many times faster than a classical computer. What we have to remember is that all of those results getting the headlines at the moment are in this category of NISQ. They're not general purpose quantum computers. They don't have the full promise and potential that we expect quantum computers to one day have. Instead, they generally solve very specific problems that are rather contrived because they're designed so that they can work today. But a consequence of that is that they generally don't do anything useful. So we were hoping to be able to find something in that category and then turn it into something that now does have a use. And it turns out that there is one such NISQ-era problem that we were able to make this work with called boson sampling. And this is one that's been demonstrated in numerous places all around the world now and well published. Some of the leading groups in the world in this field are primarily the Chinese group led by Zhenwei Pen. There's a private sector company Xanadu. They've in the past built devices that do this as well that you can access in the cloud. This is all technology that's readily available today. And all that boson sampling is an interferometer, which is you have some input ports, you have some output ports, and then you have some beam splitters in there, and they cause all sorts of interference between the electromagnetic waves passing through it. And that's a quantum interference. It's one that doesn't have a classical analog. And it's very simple to build, which is why we can do it today. And it's been built with 100 or over 100 input and output ports on these devices. So what's the interest in this boson sampling problem? People originally really started looking into it because it's something that's simple that we can build today that demonstrates quantum advantage, but nobody really found an actual utility for it, any use case. And so it's been sitting around as something of academic interest for a long time. We never really had much to do with it. So in these devices, what the way of thinking about the problem that it's solving is a little bit different than normal computer problems that we're familiar with. Normally, when we think about computer algorithms, we just innately think of what computer scientists call decision problems. A decision problem is where you ask an algorithm a question and it just gives you a yes/no answer to it. So it's a very black and white answer. This is a different type of problem. This is what's called a sampling problem. And in a sampling problem, you don't ask it a question and then it gives you the answer. Instead, you ask it a question and then it has some probability distribution at the output. And the goal is to repeat that algorithm many, many times over, and each time you sample what the output is. And you build up statistics. So sampling problem is one where your answer is a statistical one rather than a yes/no outcome to a question one. Nonetheless, this problem being defined in that way as a sampling problem, this is a problem that classical computers simply cannot do efficiently, even for not that many photons. So if we put in just, say, 20 photons into an interferometer like this, simulating the output statistics is already really, really computationally hard. And the reason for that is because the output probability distribution is related to what are called matrix permanents. These are a class of computational functions that are very, very hard to evaluate and require a lot of processing time. But in this implementation, if you build it quantum mechanically using real photons as opposed to a classical simulator, you can get tremendous quantum advantage. The problem with boson sampling is that we can't use it directly in place of the hash function that we described. We need to think about how to mold this to try and make it compatible to work in a way analogous to what proof of work was doing. So in this top figure, here I've drawn the full output space on the x-axis of all of the different possible combinatorics of where 2 photons entering the device can come out across 6 different output ports. Those are all of the exhaustive combinations on the x-axis, but the number of those combinations grows exponentially, or rather super exponentially, as you start increasing the number of ports and the number of photons. But in this small case, we can just write it out explicitly. And the problem is that when you run a boson sampler, even though you're sampling from this full distribution, like the one drawn in the top graphic, you don't actually reproduce that distribution. You get a sample from it each time you run it. So if you wanted to reproduce the entire distribution, you need to take a number of samples much larger than the total number of combinations so that you can build up that distribution. But when the number of combinations is growing super exponentially, it isn't possible to take enough samples to reconstruct the entire distribution. So the purpose of the algorithm is not to reconstruct the entire probability distribution the way it's drawn on the screen. That's not what you're doing. What you're actually doing is a small number of repetitions of the algorithm, and you get some discrete points from that distribution, and that they follow that probability distribution. So with the ability to do that, the problem is boson sampling can't actually be verified. It's a sampling problem. If I gave you samples from my boson sampling device and you gave me ones from yours implementing an identical instance of the problem, we wouldn't have a way to directly compare that they are consistent with one another because we don't have the full probability distribution. However, there's a variation of boson sampling called coarse-grained boson sampling. And the goal of coarse-grained boson sampling is to group together, bunch together some of these different combinations from the top graph into buckets that combine the probabilities of multiple configurations together. And the idea is you make the number of bins sufficiently small that you actually can reproduce the full distribution, not of the underlying sample space, but of the binned distribution. And those binned distributions will converge and be consistent between multiple instances implementing the same problem, which is not the case for the normal distribution. So by coarse graining or binning different samples together, we end up with something that can be directly compared between multiple independent users repeating the same problem. And it's this basis of comparing against one another that lets us effectively say yes or no to whether people were honestly participating in the protocol. So what we're going to do to make this work in the protocol, I'll walk through this slide here that shows all the steps that go into how we combine that coarse-grained boson sampling concept into a blockchain type of concept. So starting up at 1, we have a transaction is created by the network. Okay, that was the same as last time. Then as we get on to 3, the new block is sent to every node on the network. All the nodes that want to participate, they can choose to do so by laying a wager or a stake. We introduce a wager to penalize nodes if they're dishonest and they're wasting resources. We'll come back to that in a bit. So now, once they've all seen what the transaction is, they start running boson samplers for a certain amount of time. There's a cutoff where they have to submit it by. And the way that in the hash-based version for Bitcoin that we described earlier, we were hashing the header concatenated with some random data. Here we're going to use the header and encode it into the input photon configuration going into the interferometer. So if you have a lot of input ports and a subset of them have photons in them, all the different combinatorics of which modes could have the photons, that's how we encode the previous block header. And that makes this instance of the boson sampling problem innately linked to the previous block transaction in the same way that concatenating the header with a random bit string and hashing it links that instance of the inverse hashing problem to a particular transaction. So once all of the miners have done their boson sampling, they send all of their samples to the network for everybody else to see, and everybody can now do the same calculation, looking at all of the samples contributed. All of the samples contributed are combined to create a net sample set, and then these are binned randomly in accordance with a random beacon. Now, there are different ways you can do random beacons. It can be an external random source, or it can be something internally, like a hash of the committed samples. There are different ways of thinking about it, but all that matters is that whatever the mechanism is, that the binning strategy, in other words, which sample sets go into which bin, that's determined after the samples have already been committed so that people can't just pre-calculate things. So once that's all done, then we go and we start comparing these binned distributions, and the ones that get their binned distributions within a certain tolerance threshold of one another, they're regarded as honest, and they get their stake back because they were honest, and they get a reward, which is a share of the transaction fee. In the Bitcoin network, it's a little bit different. In the Bitcoin network, when you win mining, that new piece of random data that you put into the hash function to give you the satisfying output, that's actually your coin. You've created new currency in the process. Here we're doing it slightly differently, using a system of rewards and penalties to achieve a similar kind of outcome. In our case, it's comparing these binned distributions with one another to check for who's consistent with whom, and the majority will determines what the outcome on that consistency is. So combining all those ideas together, we can do some estimates of like how much energy or speed up savings is going to be. The figure on the left is just looking at the sample rate speed up. Here we're just saying, comparing a quantum computer versus a supercomputer or a single core computer, how much faster can the quantum computer do it than the supercomputer? And on the x-axis is the number of photons. So it scales, it gets much, much harder as we add more photons. But you see, if you've got a 40 photon instance of the problem, then you've got your quantum computer being a factor of 10 to the 6 faster than the supercomputer. So these are, this all just boils down purely to the fact that the classical computers have to solve all these matrix permanents to try and simulate these distributions, whereas quantum computers comes out straight away. You can also think about the energy savings. To get a single sample of a boson sampling distribution from a supercomputer versus a quantum computer, we can see that the classical computers are expending many orders of magnitude more energy to reproduce samples compared to the actual boson sampler. So we know that a quantum computer, or rather a quantum sampler, the special purpose boson sampler, can do this much more efficiently than a classical computer. And by combining that with a reward and a penalty system, whereby you offer a wager to participate and you get that back if you complete the process honestly to the end, and you get a reward if you're honest as well. Combining those together, we end up with a blockchain which is governed by an algorithm where, just like what we have today, you have to solve a random problem where you can't pre-calculate things, you can't know the answers in advance. You have to go through and actually produce a whole set of samples. You also can't just replicate someone else's, because if we impose the condition that samples have to be unique, we can ensure that people aren't just borrowing data from one another. And that isn't a problem. You might say, well, if people aren't allowed to have overlapping data, then that must mean that only one person can have honest data. That's not the case, because what we need to remember is that the output to a boson sampling distribution has an exponential number of possible configurations within it. You're taking a small subset of those. You can't possibly sample an exponential number of terms. You randomly select a small number of them. And different nodes doing identical processes, each time they're all getting random samples, statistically, they're all going to be different. So if you just impose the requirement that if someone else comes up with a sample that has already been used, then it gets excluded, it doesn't count anymore, that prevents information from being pre-calculated, shared in a dishonest way to get advantage, and it doesn't, in the context of a sampling problem, undermine anything, because in this exponentially large sampling problem, everybody's results are expected to be different anyway. So at a theoretical level, all these different bits and pieces, they fit together. We've got the basic building blocks we need. We've got a hard function that has quantum advantage. You can't pre-calculate it. It's uniquely linked back to a previous transaction. There's a way of verifying it to check that different nodes contributing samples are consistent with one another. How many samples do we actually need? That's the other question, because in the case of inverse hashing, it's just trivial. Whatever that bit string is that you put into the hash function, that's it. However many bits long that is, but it's a small number, a few hundred bits. But here we've got samples, not just a pre-image to a hash function. We've got some number of samples. How many samples do we need if we want to be able to do this verification? Well, this plot here on the screen at the moment shows this. On the x-axis, we've got the number of samples. And on the y-axis, we've got what's called the total variation distance. This is a measure, a distance measure used to compare probability distributions. So 0 TEVD means that two distributions are identical, and if it's bigger than 0, it means they're further away. So here what we're comparing is we're saying we've considered an instance of the boson sampling problem, and we've taken a case where we know exactly what its bin to distribution is analytically, and we're going to compare that perfect ideal probability distribution with samples coming from that distribution as a function of the number of samples. So it's basically saying, how many samples do you need to get a certain closeness in approximation of the actual probability distribution? And we see that it's quite a lot. On this x-axis, we've got a log 10 scale. So 10 to the 6, that's a million samples to get sort of towards the end of that tail, where those samples are very closely representative of the expected probability distribution. So the exact number of samples that you're going to need will depend ultimately on how much confidence you want to be able to differentiate between nodes honestly or dishonestly in executing the protocol. If we can tolerate big error margins and that they can be quite far away from one another, you don't need many samples. But if you want different nodes implementing the same boson sampler to come up with binned probability distributions that are very close to identical to one another, we might need on the order of 10 to the 6, 10 to the 7 samples. So this is a significant communications overhead, unlike the hash version where it might just be some small number of bits. Now we've got millions of samples. So this is a communications resource issue that's come in a sort of trade-off compared to some other things that we're saving. We're able to reduce energy consumption. We're able to get enormous advantage compared to classical computing. The problem associated with that, though, is that we need much more communication to be able to prove that we passed that test. So the other issue then is that a boson sampler is a physical device and it's not a digital one. It's a quantum mechanical one and susceptible to noise like everything. So we don't sit in an environment like hash functions where I give you a bit string and it's either right or it's wrong. We're dealing with analog kind of results given by a whole bunch of real numbers, not just bits. So what about noise? As we introduce noise, what that means is that it takes much, much longer to converge, and it doesn't perfectly converge. If you're comparing, as per that picture, the ideal distribution with samples taken from the ideal distribution, by definition, over time, it has to converge perfectly. However, if you're comparing different instances of the problem, they won't converge perfectly. And that difference in where they converge to is what's our discriminator between believing whether people did or didn't honestly execute this particular boson sampling implementation. So a brief summary of what the different bits and pieces are here. What we found is that boson sampling is a quantum era problem with quantum advantage compared to classical computers. It's one that a quantum device can do much more efficiently than a classical device. And if you mold it around a little bit, even though it's this weird sampling problem rather than a decision problem, we can coax it into acting in an analogous way to hashing, whereby you have to process a lot of data and by chance, you come out as a winner in accordance with the statistics of the samples you made. So a network, when it's actually constructed, needn't just be quantum samplers. It can comprise both classical and quantum hardware, where the classical hardware is running a numerical simulator of what's going on. The quantum sampler is actually doing it and getting it much more effectively. But this is useful in allowing a transition as this technology evolves. If we were to have a functional implementation of this with, and suppose hardly anybody had any quantum hardware at all, or nobody had any quantum hardware at all, we'd be able to still run this as a classical network using classical simulators instead of boson samplers. You would adjust the difficulty accordingly for that environment with that many classical simulators. And as quantum samplers, quantum hardware became more ubiquitous, people started owning it more, then you could start increasing the difficulty and shifting the market of nodes from being incentivized using classical hardware to shifting over to using quantum hardware, where they're doing the same problem more efficiently. So this is certainly demonstrates that in principle all of this works, all of the ingredients are there. The question is, would you do it? And why should you do it? Well, the energy saving is one issue. The communications overhead was the other trade-off that went, unfortunately, against that. But there are ways of compressing that. But the real interesting question is, what do we want to do when the classical networks become so inefficient, like the Bitcoin network, that it's just a completely unscalable approach? The answer is that's not the way to do it. We need to shift over to more efficient means. This is one potential avenue. And it may or may not be the solution. It's not to say that the Bitcoin network is going to throw away inverse hashing and switch over to quantum proof of work, but it gives us a different avenue for thinking about how we design these one-way functions to begin with, so that they can operate in an environment with both types of hardware, which will over time naturally incentivize it to shift towards quantum hardware. Thank you very much.